So in Calc 1 or, let me just adjust that. In Calc 1 or Calc BC or Calc AB, whatever, maybe Calc AB. I don't really know how the curriculum is. But point is, you've worked with the idea of tangent lines and linear approximations. If you had a function that kind of looks, like whatever, like a function, you can essentially find the tangent line. If you know the point, if you know this point, x initial, y initial, and you know the derivative, well, you can write an equation for the tangent line. And this is really helpful because you could see really near, right? If you had a point like right here, or if you had a point right here, right, you can approximate, right, points really near the initial x initial, y initial. You can approximate using your equation of a linear line, because it roughly kind of follows, if you zoom in real close, that function is gonna look a lot like your tangent line. In the same way, we can use a tangent plane to make approximations for 3D functions. So if we think about drawing this out, like at a point right, let's do right here, let's do maybe, I guess this point right here. It's gonna be very hard to kind of tell, okay, maybe this wasn't the best, right? Maybe you think about a point right here. Also doesn't look good. Maybe I need a... Point is, maybe the tangent line at this point, the tangent plane at that point right there is going to be some plane that kind of just barely in the same way the tangent line just barely touches the function, the plane just barely kisses the 3D function, and you can use it as an approximation. Let me show you with my book. Let me show you what I'm talking about. It doesn't make as much. It's hard to draw, in all honesty. That's kind of the hardest part about teaching MB Calc, is just it's hard to draw. But you can see, hopefully, if I've done this right, this tangent line just barely touches the function. It touches the function and it approximates. And you can even see, if you were to zoom in, the function looks more and more like the plane. That's kind of the idea with a tangent plane. So the tangent plane is defined pretty simply, because if you think about it, there's going to be at this point, if you were to there's going to be really there's going to be a tangent line in the x direction and a tangent line in the y direction. Because we think about for this function, right? If this function is f, f, there's going to be some sort of partial f, partial x, and then there's going to be a partial f, partial y, taking partial derivatives with respect to each variable, and these derivatives tell us the slope of a line that if you were to put a cross section through. So for example, in the x direction, if you were to put a cross section with a plane y equals, right? If you were to put a plane like so, the cross section would be some sort of curve, and at a certain point, the tangent line to that curve would have the slope partial f, partial x. Same thing for partial f, partial y. So if you have both of those tangent planes lying on that plane, essentially what you get is pretty plain and simple. If we think about the definition of a plane, L, X, Y is going to equal partial f, partial x, x minus x initial, plus partial f, partial y, y minus y initial, plus z initial. Well, the tangent lines to the tangent lines to the curves of the cross sections, when you do that for the function, those partial derivatives end up being the same partial derivatives for the plane. So, these for the function, so if this was really, you could just leave it like that. The general form for a plane is just its partial derivative. So really the general form for a plane is partial L, right? It's the derivatives of the plane, but the derivatives of the plane, match up with the partial derivatives of the function for the tangent when it's at tangency. So I will write a partial f. And then you need to know the point at which you're going to have the tangent point, or tangent, the point where the plane will be tangent with the function. So what we can do is find, let's say we have a function that's z equals ln, let's do x minus 2y. Well, let's find what would a tangent plane look like that. Look for this function at, let's say, 3, 1, 0. So that exists on the point, right? So 3, yeah, that works. Okay, so first we can do partial z partial x. Oh my god, I wrote a d by accident. Whoopsies. Should be the partial symbol. Partial z partial x. And I'm taking the derivative with respect to x. So I would do chain rule here. So 1 over, right? The derivative of ln is 1 over. So 1 over x minus 2y times derivative of the inside. For x, it would just, be 1, right? The derivative of x is 1. So multiply that by 1. Is this the same thing? I can do the same thing for partial y. So partial z partial y, 1 over x minus 2y, multiplied by negative 2. So let's sub in. So if I were to take I'm taking the partial derivatives at this point, right? The derivative will change, the partial derivative will change all over the function. So I need to find the partial derivative at the point of tangency. So at x equals 3, x equals 3, y equals 1. So 1 minus 3 minus 2, 1 would equal 1. Same thing here. I'm not going to do the nice notation because I'm lazy. But negative 2 over 3 minus 2, 1 should equal negative 2, right? Because the bottom turns into 1. So my final answer, right, I would have my L, X, Y. You could do plus the initial on the other side or do minus the initial on the L side. So z, or L, X, Y minus z initial, which is 0, is going to equal partial z, or partial f, partial x, which is, in this case, 1. So 1 times x minus 3 plus the partial derivative with respect to y is negative 2. So minus 2y minus 1. If I were to clean this up, I would get L, X, Y equals x. Distribute. So minus 3. That would give me plus 2, so it should be x minus y. This should be maybe negative 3 plus 2. This doesn't seem right. Oh, because I'm distributing. Yeah, okay, it's x minus 2y plus 2. For some reason, this feels wrong, which I'm not sure why. And I didn't write my answer down. So this could be wrong, but I know it should be x minus 2y, and then I think minus 1. Right? Yeah, I think that should be fine. If I plug in 3 minus 2 is 1. Yeah, should be right. Okay. Cool. So this would be the tangent plane, and I could plug in points. Like if I were to plug in 3.3, I could plug in 3.3 and 3.3, 1.3, right? I could plug in 3.3, 1.3, and I would get an approximation. So that's essentially tangent plane and linear approximations. Another concept that's just kind of tied to this whole idea is something called the differential. So there's this thing called the differential of a function. So if you think about dz, so dz, the differential would be partial f. Okay, let me do it like this. Let me make it bigger. So if I think about the differential dz will equal partial z partial x. Oh my god, partial z partial x times dx plus partial z partial y dy. And what this equation kind of tells us is, the way I like to think about it is like, what is my change in z for a given change in x and change in y, right? well, your z value, like if you think about a function, let me just get a function going here. So if you think about a function like, so, I don't know, just any surface, right? My z value can change in two ways. I can go in the x-axis, or I can travel in the x direction, travel in the y direction, or both. So my total change in z, right? If this is z initial and this is z final, my total change in z, my delta z, will equal my change in x multiplied by partial z partial x. Because remember, partial z partial x tells us how much does my z value change for a certain change in x. So it's like this kind of ratio of like my z changes this much for this much change in x. Multiply that by the change in x, I get my change in z. And then same thing for the y direction, right? So this gives me the total change in z for both moving in the x direction and the y direction. Now, it becomes more and more and more accurate as my change in x and y approaches 0, where dx and dy, that represents those very, very small changes in x and y, and that gives us that, right? It gives us the total change in z, dz, which will be very small, but we call this our differential. So let's do an example of just finding differential. Not a crazy concept if you know how to take derivatives. So let me just think about, let's do z equals e to the negative x sine y plus 2x. Is that the right thing? Yeah. So let's find the differential dz for this function. So partial z partial z partial x, we're gonna have to use product rule here. So I'll take the derivative of this is negative e to the negative x, and then I don't take the derivative of the other. And then I take the derivative of the other, so e to the negative x, and then so I'm gonna do chain rule, so cosine y plus 2x multiplied by 2. So in the end, I really get this times 2, I can just say is plus 2, e to the negative 2x. And then partial z partial y, I can take, this one's even easier because I just treat the e to the negative x as a constant. I don't even need product rule, I just need chain rule. 2x and then multiply by 1, right? Because the derivative of y plus 2x is just 1 with respect to y. So my final differential will look something like this. So I can say 2e to the negative x cosine y plus 2x minus e to the negative x sine y plus 2x. Oh my god, okay. All of that times dx and then plus e to the negative x cosine y plus 2x dy. So that's what my differential will look like. Not a crazy idea. But yeah, thank you for watching. This has been tangent line approximations and tangent planes and linear approximations. Yeah, there we go. Yeah, thank you for watching.